So now that we've designed our CPU, we want to be able to write some assembly language code and see how it operates. So that's what we're going to do over this video. I'll get into a bit more detail in this example than I would normally. It's just to get you started, and it'll allow you to then write some more code for yourself. So if you go ahead and open up the assembler debugger, you'll have a page like this here. Now what we can do is, if you clear everything off, just press the clear command here, and you'll see everything is set to 0. So what we're going to do is count to 10. So we're going to have one of the registers, and we're going to count 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So let's go ahead and we'll do that now. So the first thing we're going to do is put in the counting value. So the counting value is going to be a value of 1. So that's the difference that we're going to put in. So it counts in steps of 1. So we're going to put 1 into R0. So you can press the assemble, and you can see when you've assembled that, we've got the machine code here for the op code, which is data R0, and the machine code here for the data, which is a value of 1. So when we press debug, you'll see it puts the value of 1 into register R0. Now we're going to have an end point, so I think we'll actually, rather than count up to 10, we'll just count up to 3. It means we can fit it in the screen here and you can see it a lot easier. So let's say the stop point is actually 3. So we're going to put our value of 3 into register R1. So we assemble and debug, and you see we've got a value of 3 in register R1. So now if we wanted to, we could use the add command, and we could add the contents of R0 onto the contents of R3. So what this does is it adds R0 to R3 and it puts the value in R3. Now at the moment R3 is a value of 0, so it just adds 0 and 1 and it puts it into R3. So let's check that and see if it works. So we've debugged it, we've assembled it and then debug, and you'll see it's put the value of 1 into R3. Now one other thing to note here is that this is the add command here, and in the add command it's an ALU instruction, and the ALU instruction affects the flags. So really before we do an ALU instruction, what we want to do is make sure that all the flags are set to 0. So we'll clear the flags off, use the CLF command, and then we'll do the add R0, R3. Now we don't always have to do this CLF, but it's good practice to do it, just in case there's any other flag set that gets carried over from a previous ALU instruction. So we'll assemble this and debug. Now I tend to work through each line of code at a time, and it keeps me right and it makes the actual design of the code a lot easier. So you can see here that it's set all of these flags to 0 at the CLF instruction. So now if we wanted to make the value for R3 a value of 2, well all we would need to do is add R0 again onto R3. So we would add another 1 onto R3, and we assemble and debug, and you'll see R3 becomes a value of 2. Now we could continually do that, we could add another one on, but of course that's not a very efficient way of doing it, and the point is that what we want to be able to do is have a loop that will do this add instruction for us. So let's go ahead and we'll see how to loop this. So let's get rid of these 2 lines here. Now after we've done the add, what we want to do is compare and see whether the value at R3 is actually equal to the value of R1, because then we know we're at the end of the code. So we can use the compare command. So that's CMP, and we'll compare R3 with the value of R1. We'll just run through that now, assemble it, and then debug. Now, whenever the value for R3 is equal to the value of R1, we know that this is the end of the program, and we really want to jump to the end of the program. So we could say jump if equal. Now we've got to jump to the end of the program, but we don't know where the end of the program is for the moment, so we could just put question mark in here. Now if the compare is not equal to it, then what we want to do is jump back to the add instruction. So what we can do then is just use the JMP, which is the jump, and we can jump to the address given by the add instruction. So we have to work out what that address is. And then finally we can end the program, so we can just put in an end command. Now the interesting thing is here we have to try and work out these values here for these addresses, and we have to do this by hand and eye by ourselves. Now later on, whenever we start looking at labels, we'll realise there's a much smarter way of doing this, but for the moment we want to try it like this. So if we want to jump back to the end of the program, then the end of the program is this point here. But this point here is an actual point in memory, and that point in memory is going to be given by some memory address here once we actually assemble the program. But if we were to start at this point here is going to be memory location 0, so that opcode is 0. And then this one here would be memory location 1. So it's going to run 0, 1, and then it will go 2, 3, and then it's going to go 4. There's nothing here in this one, so it will go 5, and 6, and then 7, and then there'll be an address in here which will be 8, 9, 10, and 11. So it means that the end of this program here is actually going to be at memory location 11. So we can put in there 8, 9, 10, 11. Now whenever we jump, we want to jump back to this add instruction. And again we can count along again. We're going to go 0, 1, 2, 3, 4, and it's 5. So that's the memory location 5. So we can put in our value for 5 here, 1, 0, 1. So this is our final code here. Now what we'll do is we'll assemble this. And that's us assembled it here. And you can see it's going to take 1, 2, 3, 12 bytes. So we've got 12 bytes is the length of our program in order to count from 0 to 3. And you can see here now that these jump addresses are going to be given by the addresses here in RAM. So let's say for example we said that the end address is going to be at address 11, and you can see that's true. That's going to be memory location 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and that is the end command. And again the jump if equal to this the jump command here, going back to the add, well the add we said is going to be at position 5, and that is 0, 1, 2, 3, 4, 5, and this one here is the add command. So we're going back to this point here in memory. Now you might be looking at this and saying, well that's not a very efficient way of doing this. What we really want to be able to do is just to put in labels. So rather than have jump to the actual address, we want to be able to say something like jump to, and we could replace that with a mnemonic like for example loop 1, and we could change, well this one here we change to mnemonic would be end, and this one here we could change to some mnemonic saying the beginning of loop 1. But at the moment we're not able to do that within this assembly language, and there's a reason why I didn't want to do that, because I want to build up all of these ideas separately so you can see where every single part of an assembler is needed, and that means that you can actually work it out for yourselves. So let's run through this code here. So we assemble it and then we debug it, and you can see it starting to count. CLF, add, compare, and then it jumps back to the add, and then jumps back to the add again, and finally it goes from the jump if equal to the end, and you can see it's now ended and it's counted 1, 2, 3. So I'll allow that to run once more, and again you can write this out yourself and give it a go. And as I said, I'm talking through this in a lot more detail than you maybe require, but it's just for this first one, just to get used to the using this assembler debugger. Now a few other things here to note. Over at this side here, you can see that we've got the actual registers. So we've got the instruction register. So the instruction register contains the instruction of the current that is currently being ran. So at the moment the instruction register contains 33, and that's going to be the opcode for the actual data R0. Now another thing to note is the instruction address register. Well, the instruction address register doesn't actually contain the instruction of the present address. The instruction address register contains the address of the next instruction that you're going to fetch in, because that's how we've designed the fetch execute cycle. It prefetches the very next instruction that you're going to use. So this is actually pointing to the next instruction, which is address 2, and that's correct because we're going to go 0, 1, 2. So this is the next instruction, and the instruction after that is going to be 0, 1, 2, 3, 4. You can see that address 4 is the next instruction, and one after that will be address 5, and then 6, and then it'll be address 7, 8, 9, and then after that will be 10, 11. So it counts in that order. And you can see the steps here running through 1, 2, 3, 4, 5, 6, 7. So it runs through the first 7 lines here, and then it jumps back to line 4. So this is line 4, which is the add, and then it goes 5, 6, 7, 4, 5, 6, and then it's at that point there the jump equal is true, so then it jumps to line 8, which is the final line here, which is the end command. So that's me talk through this in a lot of detail. Let's go ahead and we'll export this, and we'll run it up in our actual CPU, and we'll check and see whether all of the registers and flags match with what we have here. So you can press the export, and you can put the path to where you want to save the file. So I've got my path here. Control C, Control V. Now that's saved this here, which is the output, which is the program. I'll have saved that in hexadecimal in a file called mysim. So let's go ahead and we'll load mysim into the CPU and we'll see it running. So go ahead and open up Logisim, and then open up the CPU design. Head down to the CPU test and double click, and you should have this page here. So let's go ahead and we'll load in our program. So in order to do that, what we have to do again is ensure we've got the little tick here, and ensure we've got the little finger here as well. So if you click on reset, and then click on the reset, which is over here, you'll see it's reset all of the registers to 0. And also you note here the flags as well. You've got these as setting at 0, we've got A equals B, and we've got 0. Now you can see the A equals B if you drop inside. It's going to be A equals B because initially it's starting off with 0 in at the ALU, so whenever it adds up it gets a value of 0, so this 0 flag is going to be set. Now what we want to do is load up our program, so we right click and we click edit contents and we open up the file. Now the file again is called mysim, so click on that, close the window, and you see that our program is now loaded into this external RAM. So now what we want to do is load the program in, so you click on our tick enable, and what we'll do is we'll just stop this whenever it gets up to round about FF. So as soon as you see an F appearing here, you can just stop it. And this is us loading up the code now as we speak. So we've stopped it at FB, so what we'll do is we'll just click along until you get to FF. And that's us now sitting at 0 on the bus. So we've loaded up the code into the CPU, so you can drop into the CPU and you can have a look and you'll see the code actually within the RAM. So now what we want to do is compare all of these registers and the flags with what we got whenever we did our assembler. We looked at our assembler debugger. So let's go in and we'll fix this page up for us. So here we go. I'll get rid of my image here as well. So what we've got is the CPU at the top with the registers and flags. And if you get into the assembler debugger, in the second page of that, there's a tab there that's called debugger output in hex. So if you click on that, all I've done is taken the registers and the flags and I've output the values in hex. So it's just the same as the debugger page, but in hexadecimal, because the output here in the registers is going to be hexadecimal and it's much easier to make a comparison. So what we want to do is count through, and you note that whenever we get to instruction IR31, instruction register, the value in it is 21. That's us went through the first fetch execute cycle, so that's going to take 24 clock pulses. So that's me counted through 24, but it's going to be a few clock pulses further along because of this prefetch. So if we count along until we get the 21, so that's us now. We've got 2, 21 and 1, so it's 2, 21 and 1. Now we don't care what the flags are because it's a data command, and a data command isn't going to, we're not going to run any jump function off of a data command. We're only going to run any jump functions off of the ALU instruction, so we don't really care what these say. And again, we can head up along 24 clock pulses, so if you click this 24 times, you'll see that the next command has come along, and again it's 4, 60, 1 and 3. You can see 4, 60, 1 and 3, and then we'll go along to the next one. And you see we're going to get the instruction 583, 1 and 3, 583, 1 and 3. And you can see at this point here, all of the outputs here are sitting at 0 for the flags, and we've got all of the outputs 0 for the flags here. So let's head on to the next instruction. And you can see we're now at instruction at 6 FD131, so we've got 6 FD 1, 3 and 1. And now if you check out the flags, we've got 0, 0, 1, 0, 0, and that's 0, 0, 1, 0, 0, so we've got the A greater than B. So we can continue doing this, and as we continue doing this, you'll see that it's going to map out exactly what we have here. So I suggest you work through a few of these yourself, and you can see that the flags and the registers here should match the flags and the registers up in the CPU. So let's just run through the CPU from the beginning to the end here. So I'll head back up to this page here. So what we'll do is I'll just continue the running, so I can actually click on if I zoom out here, I can click on the simulate and I can click on tick enable. Now whenever I do that, it's just going to start running through and you'll see it going to value 2, a value of 3, and then whenever this little red light comes on here, that means we're actually at the end of the code, and you can see that we've counted to 3. Now what we can do is we can then stop the clock. You come in and go to simulate and tick enable, so the clock is now switched off. So that's us back, and that's us finished our code. And the final command here is the stop command, which is always going to be a value of CF. So let's go ahead and we'll reload the program, and I'll just let it run all the way through. So in order to do that, we're going to have to go up into simulate. We'll have to press reset for resetting the simulation. We're then going to have to go to the reset button here, and that's it, reset back to 0. And then we can load in the program again. So we right click, edit contents, open, and we open our file. Close window, that's our file loaded in, ready to run. And then we can click on the simulate, and we can click on the tick enable, and whenever we click on the tick enable, it will start running up. So I'll get the page back for us here. So tick enable, and there you see it starting to load up, and when it gets to FF, that's it fully loaded, and we'll see this counting 1, 2, 3. Now maybe not the most exciting code, but it's a start, and what we want to go on and do from this is to start building other simple mathematical functions. So you can see it's counted 1, 2, 3. So that's all there is for this video. I went into a bit more detail than I would normally. I just wanted to make sure that you understood all the parts of the assembler and also how to run our code in the CPU. So we'll go on in the next video and we'll look at some more complicated coding, and we'll run through it a lot quicker than we did in this video. So thank you for listening. I'll get you on the next video. Goodbye.